published articles, of which he's the first author of 60 in 20 research projects. This is really impressive. So without any further delay, the floor is yours.
Thank you very much. Thank you for your introduction. And then it's really nice to meet you here. And I'm really honored to get invited for this kind of good seminar to introduce my research here. So today's talk is about immersive audiovisual 3D scene reproduction in virtual reality. But I heard from Anna that the background of the people here are very different, mainly probably linguistic and languages and some other. So I'll stay very high level of introduction, and but still we probably share the same kind of common interest. Like I'm very interested in interaction, in virtual remote environment, also in interaction between man and robot, that kind of stuff. So, but to be honest, I don't know how I can give, what kind of insight I can really give you, but hopefully you can find out some interesting part. And then probably it will be really great if you use more link. Right? Okay.
Just click here.
Yes. Yeah, my keypad is not really working. I don't know. Right. Just let me just shortly introduce my background. So I have some research experience in different countries and different areas. So for 4 or 5 years during my PhD, I also worked at the Image Media Center in South Korea. I'm originally from South Korea. And then I developed some 3D display and also for 3D visualization, more like immersive kind of a 3D stuff. And then after getting my PhD, I moved to Japan and then worked at ATR. It's like more like a telecommunication research center. And then Learning Science Lab, there I developed some 3D human monitoring systems for hospital application, like monitoring the staff and patient movement in 3D using different sensors like RF tag and then also videos and different sensors. Then in 2008, I came to the UK and then joined the CVSSP, the Center for Vision, Speech and Signal Processing at the University of Surrey. This is the largest vision research group in the UK. And now 170 PhD students and academics are working only on computer vision and some speech and signal processing. So it's a really huge center. I worked there as a senior research fellow for 12 years, and I was involved in more like a film production and media industry. And then I joined the University of Southampton in 2020. Right? And then my research interest, as Anna introduced, for 5 years, my research interest was really focused on 3D computer vision, including some 3D reconstruction from 2D images and virtual and augmented reality, 360 image processing, and audio-visual data processing, and also this work is not just my own, but also collaborating with my PhD student and my current PhD student. Probably, yes, some of you can recognize this guy, Peter Hardy here, who gave a talk last week about 3D human pose estimation. So in my talk, I will just remove that part, as he gave a really talk with me last week, I believe. Anyway, my research this audiovisual reproduction research in virtual reality was started from digital questions. When I started this research, I searched some images on Google about virtual reality and metaverse. And then these are the images I got. But here, all users seem to be quite immersed in that kind of nice 3D views and then this virtual world. But there's something missing. When I researched 3D vision, I always felt like something was missing there. Probably you can find out that they are not wearing any headphone or anything, so they are not listening anything. So they are just looking at the scene as 3D, but they are not listening anything. The audio part is missing there. Yeah? So definitely, we perceive the world we rely on both audio and visual information together from our eyes and ears. So we get all information simultaneously, and our brain combines all information together, and then we interpret the world and understand the outward. But interestingly, comes the visual part and audio part in engineering. They are quite split clearly, and they don't really work together. And to be honest, they don't like it. There might be a bit more like a political reasons and then lots of things. But yeah, I also worked with audio people for a long time. It was really, really hard. It is a bit strange, but definitely we need both information to get a better interpretation and also visualization of that. And then it's a kind of trivial. There's a research that definitely special temporal synchronization of sound with visual information improves sense of presence in VR environment. Yeah, it is quite trivial, right? But surprisingly, engineering people, they don't really work together so far. So I'm really trying to bridging that kind of gap in two communities. And I also need to introduce the concept of 3D vision and 3D audio here, because many people, actually most people, misunderstand the meaning of 3D vision and audio. Because currently, so-called 3D vision and audio system, if I ask people, they just simply imagine that, oh, 3D, 3D vision, I know that. I watched this 3D TV. I tried some 3D film with the glasses in the theater and a movie and cinema. Yeah, they think that is a 3D, but actually they are not. We don't call it 3D. Actually, vision researchers, we don't call it 3D. They are still just 2D, only with depth, sense of depth. They look like popped out. Okay, those sound like 3D, but if it's a real 3D, if I move this side, then I should be able to see the side of the world. Yeah. And if I move around, the sound and the view should be changing. But actually, no. Even though they are sitting like that, and then they feel like, oh, they're really immersed, but actually they're looking at the same thing from any viewpoint. You know? So it is they don't give any degree of freedom to the user. It is not full 3D yet. And even for sound, people think that, okay, I experienced with some 5.1 hi-fi audio surround channels, and then even in cinema, you can listen 22.1 channel, really nice sound there. And they think they are real kind of 3D audio, but actually they are not. It is actually possible to set up some proper 3D audio with a 5.1 channel stereo hi-fi system like that, but it is extremely difficult to set up properly, to listen properly with the audio. I will mention I will show you this one a bit later. So there are many different concepts and the level of kind of 3D vision and audio. So the early stage one is this kind of stereoscopic display and stereo sound with like left-right signal. Actually, this stereoscopic display is the same as this kind of 3D TV one, splitting left signal and right signal feed into your left to right eye, and then they merge it to give some sense of depth. Okay, but as said, they are just kind of we call it 2.5D. That's 2D plus depth. Yeah, so it does not give any freedom to you. A bit more advanced one is like a 360 imaging. So 360 imaging with omnidirectional camera is getting common now, and with your VR headset, you can also see around the scene. So with this kind of 360 imaging, you can just have a full, you can just watch the full environment, and then you can really look around. So it gives us some degree of freedom, at least the 3 degree of freedom, like rotation. Rotate your head, and then you can see the properties from there. And also, there is an audio technique called ambisonic audio. Normally, the first order ambisonic audio is composed of like 4 channels, not left, right, but 4 channels with ambient sound and an XYZ signal, audio, and then they can give some proper direction of sound to you. So it can provide some degree of freedom to you, but still, it is not enough. So now, most realistic solution for full 6 degree of freedom, like translation and rotation. The most realistic solution is VR headset and also headphone-based one, so binaural audio. So VR headset, probably some of you have experienced VR headset, especially for young students who definitely, yeah, they should have played some VR games. like that. So there you can navigate in the scene and then move around and then look around the scene. So you get some full degree of freedom. And I'm not sure how many people experience binaural audio. Have you, anyone experienced binaural audio? So now you can easily experience this binaural audio. Just go to YouTube, search binaural audio sample, and then there will be lots of video clips. And then try to listen the sound with headphone with the proper left-right side on your ears. Then binaural audio provide correct sound which should be fed into your left ear and right ear. So they generate that sound and provide that one. So you can really feel some kind of whisper just behind you, or like birds just flying around on your head. You can clearly see the direction of sound from there. If you have not experienced that, try it. That might be very interesting experience. So that is kind of 3D audio. You can clearly listen, hear the sound from some proper direction, and then good kind of reflections, like a direct reflections, and also some reverberation. So binaural audio can provide this kind of a bit better sense of the audio. But problem of this one is very personalized display. You need a headset. You cannot really share that with other people. And also with headphone, you can only just listen to sound. There's some like a gadget-free system, like a tape system with some wall-based one with some 3D display or some holographic display. This is kind of ultimate 3D display, but problem of holographic display is that there has very little progress for last 100 years in their technology. It's extremely hard, and then it's very hard to digitize the data. Anyway, holographic display is one solution for full gadget-free system. And also in audio, there's some more progress in like object-based audio. Probably you have heard about Dolby Atmos. So Dolby Atmos is object-based audio to render the proper 3D sound in your environment. But current Dolby Atmos does not really provide proper technical coding because the audio source should be recorded with that format in that space. So it is still quite complicated. And also there's some kind of personalized sound bar system. We're using some speaker arrays. So they make some kind of, so normally the problem of sound is that once you play the sound, it propagates everywhere and then reflect and then observe and then scattered everywhere. So in the listener position, your sound is all just mixture of reflections and a mixture of some different scattered and some messed up signal. So, but in this kind of a speaker array system, they make the sound as kind of form of beam, so directional beam of sound. They can track the listener and then make some beam for left sound and right sound to your ears. So one of speed-up company in Southampton, they are developing this system. Anyway, normally 3D vision, 3D computer graphics, and 3D visual content is relatively easy to make. You can make some 3D model using computer graphics. Okay, that's fine. But 3D audio is more difficult. And then we put and input and generate. Because as I said, it's just a progress everywhere. The best way to reproduce acoustic of space is measuring room impulse response. Room impulse response is kind of a signal, which is if there is some kind of signal, peak signal at one point, and then this is the listener position, then if there's a gunshot bang, the sound arrives first here with direct sound, and then next sound will arrive via this wall, and then probably next sound might be from here, this reflection. Next one will be this reflection. Next one will be this reflection. They are first order reflection, and then second order reflection coming. So they are arriving like that. So it's kind of analog signal. With just one peak signal, you receive this kind of wave of signals like that. So problem is that this room impulse response can represent the whole room property, acoustic properties, but they correspond only to that point, from that source point to that listener point. If the source is moving around and the listener is moving around, then room impulse response is also changing. So it is very hard to measure the full room impulse response of the place. But good thing is that yeah, the assumption that I have here is that our listening system, human listening system, is not very sensitive to recognize very small change of environment or small change of sound. So our vision system is a bit more sensitive, but our listening system is not that sensitive. So in evaluating and designing this kind of 3D audio-visual system, we consider several factors. But when we evaluate the system, audio-visual system, it is more like a good or bad. There are several factors. So the first one is coherency, like audio-visual information should be synchronized and aligned well. So if the object is there, I can see the object there, then sound should be from there in proper time, right? So if it moves, and then sound should be moved together, right? So coherence is important. Another one is two factors. One is plausibility, and the other is authenticity. I'll explain the authenticity because it is with the external reference. So we assume that we know what the actual sound is. So we have the reference, ground truth signal. So the sound must be sounded like that. We know that, and then we just see that how the synthesized virtual sound really match it to the original sound of that. For example, in AR, augmented reality application, we are listening actual sound in real space, and the virtual sound is augmented in the scene. So the sound effect should be really matched with all the sound of real sound, because we have external reference. So that is authenticity. So the generated virtual sound must be matched to the original ground truth signal. So it is slightly difficult to make like that. The other one is plausibility. The plausibility is that it is just only from my own internal reference. So I don't know what the real sound should be, but if it sounds like that, then I'm just happy with that. So if the sound sounds like or the sounds really sound like that I'm in this room, if I feel like that, that's all. So that is kind of plausibility. So it is for like it is more for VR applications, because in VR application, the outside of the world is totally controlled, and then you are only in VR environment. So if you feel like that you are immersed and you feel like you are there, then that's okay. So that is more like a subjective evaluation method and called plausibility. Fortunately, we can use this kind of when we generate this kind of plausible sound and plausible audiovisual system, quite many people are just happy with that. So this was kind of general introduction of the 3D audiovisual system. And then just let me introduce for next 20 to 25 minutes about my actual research. But this work is like reproducing real world into virtual space with very simple shot. Just one photo of the scene, just one click shot, and then automatically generate full 3D space of this room in virtual space with some visual and also acoustic properties all together. It was motivated from just during the COVID period. It was actually I started this research before that, but during the COVID period, my motivation is a bit more like that. Because we had this kind of a Zoom meeting or Teams meeting. Even now, some people are there. So during the COVID, you had to just have a meeting without many people like that. But were you really happy with that kind of meeting? Probably this kind of seminar might be okay because it's just one way delivery. There's one speaker and then all just audience listening. It might be okay for this type of thing, or one-to-one meeting might be fine. But if it's a kind of a more like a roundtable meeting for brainstorming, that system is really frustrating, right? Because if one speaker talks and then all others should be just a bit silent, just listen. You can really just small talk with your neighboring people. And then you never get any kind of eye contact because camera is here and screen is here. You're looking at the screen, but camera is just capturing your forehead. So you never get any eye contact. And then there's no sense of direction. So we don't know other people where they are looking at, or probably some of them might just watching YouTube, just doing. Some of you may have that kind of experience. So definitely, yeah, it is not very useful for this kind of a random mimicking. This is the snapshot from photo Kingsman. So here, that film, people access remotely, but they just make some full 3D space, and then they visualize as a full 3D model there as holography, and then they could really interact there. They speak to each other. They can give some propagations, and then they can point out each other. They can just whisper to next to the person that's next to you. So this one gives much better kind of a sense of immersiveness and also freedom there, right? So I'm just wondering if how I can really make that kind of space, just like my room, make my room just with simple shot, and then make there and invite my friend there from remote. Yeah, but it should not be too complicated, like a super heavy kind of computer graphics job or that kind of things. It's too much. So is there any way to reproduce that my space in virtual space with just a simple capture? So it is still based on the assumption that human perception is not too sensitive to enough to recognize difference of small errors in geometry, or some geometrical errors, or that can change of sound there. So this is the pipeline I propose. This starts only from just one photo, one 360 omnidirectional photo. There's some camera off-the-shelf camera you can buy from Amazon and anywhere. It's a big camera with 2 feature lens. So with just one click, you can capture the whole 360 surrounding scene. So it starts only from that one photo. From there, I try to retrieve some missing depth information, because that is 2D image, but try to get depth from that. And then from depth, I try to get some full 3D geometry with their semantic kind of segmentation. What is table, what is chair, what is bookshelf, what is the ceiling, what is wall, something like that. And on the other hand, I also try to get some material property from this photo, if that is fabric or wood or plaster, brick or window, that kind of things. And then combine these two information, I model the acoustic room model. On the other hand, this one from 360 photo or video, I also try to track the human action and behaviors together. Actually, Peter is taking this part. And then they are all combined and then rendered in the real space together. So I'm gonna introduce this high-level concept of individual component here, because it includes lots of different computer vision techniques, and each task is quite huge area in computer vision. So I will just simply introduce only just a concept and idea. So depth estimation, originally before this kind of AI deep learning technique or just getting popular, there was no way to retrieve 3D depth from one single photo. It's inverse problem in mathematics. So in traditional computer vision technique, we used at least 2 or 3 cameras, or multiple cameras. If you take the shot from multiple points, and then by the matching them, actually is in the next page. The 3D point is mapped into 2D image. But if we have 2 images, and then we know the matching point, and then we can triangulate and then take it back to 3D point by just a projection. So that's the main concept of depth estimation from 2 images. And then I tried it with 2 360 cameras. It's a camera with 2 feature lens, and then it takes the shot which covers from 0 to 180 degrees vertically and 0 to 360 horizontally. And then they are unwrapped as a 2D image like that, like world map. You know, our Earth is a kind of sphere, but world map is just unwrapped and stretched into 2D, right? Problem is that we have serious distortion, especially in the top and bottom area. Like in world map, always Russia and Canada, size of them was really exaggerated, right? Because of this distortion. They have some kind of problem, but still, if we can have really good matching between 2 images, then we can get some good depth from them. But still, we don't really want to use 2 images or 2 cameras because it is too much. By 2 cameras, alignment and measuring, matching, that's too much. But owing to the progress in deep learning and AI, now we could get some depth from single shot. But the biggest problem of deep learning and AI is getting training data. Because to train your architecture, you need a huge amount of data set with ground truth. Then they can learn the data. But problem of 360 camera is that we have a really serious lack of data set. For normal photos, okay, there are lots of data set available with depth. But for 361, they have lots of distortion. So we can't really use normal image data set. So we need some ground truth for 360 images. But getting 360 depth is much more complicated than normal cameras. So we have greatly limited label data set. Therefore, we use some technique called domain adaptation to cover the lack of label data set. It is, I'm not sure if I have enough time to introduce some details. It is used when we have some enough data set for certain domains, some certain scene. Okay, for these kind of office scenes, we have enough data set, but we want to get some depth for like our house scenes, like our bedroom or living room, then they are quite different. So trained parameters for office scenes, they are not really working for, they don't really work well for house scene. So their domains are quite different. In that case, we can use several techniques like transfer learning or domain adaptation. There are a few techniques like that. So domain adaptation is one of them. If you are interested in probably, yeah, maybe I better to just skip the technical details or introduction of domain adaptation technique, but you can just read a paper about domain adaptation, how you can really train and then train some data set which has quite a small amount of data. I mean, ground truth data. And then it is also, but still, even with that one, it was very hard to find some proper source domain data. So we really get some serious lag of data set. Therefore, what we did next time was like we use a synthetic data set, like a computer graphics data set. Because in 3D world, there are lots of easy-based 3D models of the scene, like from computer games. Yeah, they all based from 3D models. We can render the scene from some 3D games or 3D models. Then we can get lots of ground truth texture and corresponding depth from 3D models. Problem is that now the domain gap is even bigger because the texture from computer graphics and real world photo, they are too different. So we need to improve our architecture with some more tricks and techniques to improve that to get proper depth. Anyway, using this kind of technique, we could get some kind of depth map from single image. So this is kind of images, and then we could get this kind of depth map. There are still some errors, especially in ceiling and floors, because there's no proper texture, and then they have serious distortions. But still, we could get some acceptable level of that. My students are working on that. The other one is the material recognition. Material recognition is even harder than depth estimation because even our human experience, it is really hard to tell what kind of materials they are. For example, this is kitchen, so it's kitchen. So we can assume that okay, this might be wood, this should be window, so it's glass, and then this might be some plaster or concrete. This should be tile. This might be metal because it's. But how about this area between the window exchange? What's the material of that? Is it tile or plaster or concrete? It's really hard to tell from our viewpoint, right? So material segmentation is much harder than other tasks like. Therefore, here our main idea was not only looking at the individual patches in deep learning, we consider global context of the scene and local texture together and combine them. Because global context can give what kind of object they are, so you can narrow down the type of materials. And then looking at some local textures, you can see that, oh, they should be wood, plastic, or they should be metal. So we designed two different kind of pipeline. One is global branch and local branch, and combine them together to get some material map. And then they are combined as this one pipeline later using some attention network, so-called transformer in AI. Transformer is one of them, this kind of main kind of a trend in AI these days. So we also apply this transformer and then could get some of the better material maps. So here, this is a result. So this is the input image, and then this is our output. So here it means that, so this is very different from object segmentation. It does recognize only materials. So this part is just fabrics, like including this sofa area should be fabric. And then this part should be wood, this kind of floor and this walls, wood. And this is glasses, like that, glass, like that. Yeah. So this is the material part. And then from depth map, we need one more step, like semantic scene reconstruction and completion. So this is another challenging technique in computer vision, like a 3D scene, semantic scene completion. Completion is different from 3D reconstruction. 3D reconstruction is more wider and then popular field. But in 3D reconstruction, they just reconstruct 3D geometry only for the visible part. For example, if you take a photo here, then we try to reconstruct a 3D model for this kind of surface, some visible surface. But the problem is that if we put this model in VR, users can move around in the scene. It means that they also want to see that the behind of this table, but there's no information from the photo, right? But in full VR scene, we need that invisible part, as occluded part. So this SSP, semantic scene completion, is tasked to infer and guess the geometry and then their object, semantic object, including this kind of invisible part of that. So this is only visible part from the camera, like from this image. Yeah. But there are some hidden part like that. So guessing this kind of geometry from this kind of only visual part. This is semantic scene completion. It is also a very difficult task in computer vision, very challenging one. So a few of my PhD students were tackling this task. So if we retrieve some depth from this image and then reconstruct the scene, and then we can see lots of holes like that. Because these holes are from the kind of occlusion. Here's a table, but we can only see the floor behind the table, right? So there's large holes. But through the deep learning technique, we try to guess and fill in the hole and then make a bit more complete scene. So, for example, this is the input, and then this is reconstruction with lots of holes, and then this is ground truth of complete model, and then this is inferred model from this is semantic scene completion. And also those colors show their object labels. Okay, so that is sofa, chair, table, floor, and then this one should be some furniture, some kind of furniture. Yeah. So this is semantic scene completion task. Next one should be, we also have this human tracking and pose estimation, but actually Peter gave his talk last week, so I'll skip this one. And the next one is acoustic room modeling. So how we can make the acoustic room. So once we get this full 3D model, then now we can simulate like a ray tracing, like putting some virtual sound source and then see their kind of their behavior in this kind of a space to make this kind of room impulse response. So it's a synthesis of room impulse response, and then they are analog signals. So we need to parameterize those kind of signals. There's some parameterization. This is how to synthesize room impulse response using this kind of simulator from the reconstructed full 3D model using some virtual sound and then virtual microphone, and then how to synthesize that. But maybe I can just skip some details. But anyway, the point is that now we can synthesize some plausible room impulse response of the space only from one foot. They must be parameterized, unfortunately, because they are analog signals. So we cannot generate infinite number of room impulse responses for the scene. They are too much. So we try to parameterize them. Especially, we are focusing two factors for users. First one is early reflections, and the other one is reverberations. So early reflection is that if someone is talking to me and then there's direct sound, but also there is some early reflection, there's some warmth here. So the sound should be, I guess, some direct sound first and then reflected sound from the wall. So that kind of early reflection is quite important to get some sense of immersiveness. And then the other one is reverberation. So even this room is, you can feel some reverberation, right? And if I'm talking in like a cathedral, you will get more reverberation. Probably you cannot really understand what I'm talking if it's the reverberation is too much. But if we are in a desert, then you can only listen only direct sound. It's a very dry sound you will hear. Yeah. So that kind of late reverberation is another one. So early reflection is just the time of arrival, like the difference of arrival of direct sound and the first order reflections. That is time of arrival. And direction of arrival is also direction of direct sound and also direction of reflected sound. So that you can get that kind of early reflection. Probably you never thought about that before, but if you carefully try, and then you can see the difference according to your position. And some sensitive people can really feel that. And then they feel a bit weird if this kind of early reflection is different. And then, oh, that sounds really weird. And then late reverberation, many people can feel it, this one. Oh, it sounds too dry in this space, or this reverberation is too much. I'll give you some samples later. But I'm not sure if you can really hear very well, but so anyway, we just implemented it in Unity, like a 3D game platform, and then rendered the scene. And then I captured lots of scenes and also recorded actual sound there to compare actual sound and synthesized sound. And then here's some comparison. But anyway, this is ground truth, and you can see them, they are still quite far from the ground truth. I'll explain the reason later. But then. So this is the space I captured, and this is ground truth. Ground truth means this is actual sound in that space. I actually played and recorded in that space. So this one should be the correct ground truth sound you should hear. And this is estimated and then synthesized sound from only this photo. And then put some virtual sound source and then the microphone there, and I just record it. And you can hear some slight difference. But problem is that if people joined on Zoom, probably if they are on proper headset with proper left-right sound, then probably they can listen properly. But here, now the sound is coming from the TV, and then they also get some influence from this room geometry already. So they are already contaminated quite a lot. So it might be a bit difficult to see the difference here, but let me just try. This is real sound in this space. And this is a synthesized one in virtual space from this one point. Oh, sorry. They have some more noise, and also reverberation is slightly different. Probably you cannot really get some early reflections. But this one might be even worse. So this is a kind of bad sample. So to see the differences, clear differences. This is ground truth in this studio hall. This is a large hall, so there are more reverberations.
I just saw Jim near the new archaeological museum.
This is what you hear in this studio. And this is a synthesized one from photo.
I just saw Jim near the new archaeological museum.
You hear more reverberations. The reason is that I try to recognize the material and the geometry of that, but the problem is that in this studio, you can see these blue panels, yeah? They are kind of soft fabric panels to observe the sound, to just reduce the reverberation. But from that photo, my architect could not really recognize that soft panels, but just the design, just model them as just concrete wall. That's why I got more reverberation there. So still there are a long way to go. Yeah.
Can you specify, for example, when you are doing it, can you modify? Or
Yes, manually, yes. We can modify manually, yes. But I'm just showing them full automatic process one, but definitely we can allow that kind of a manual user interaction, modify that to fix it. Yes. Sometimes to make some real demo system, we do it. Yeah.
one more question. I guess it also depends on where the person is standing when the sound was recorded.
Yeah, definitely,
So
yes.
in this case, the ground truth, you assume that the person would be standing in the middle of the room, or
Yes, actually, yeah, good question. In this one, we clearly measured the sound source position, their X, Y, Z position, and then we put it the microphone position, and then we put the same virtual sound source there, and then we put it in the 3D space, so that the relationship between the sound source and the listener point are exactly the same. And yes, that's true. If they are move around, they should be changed.
the estimation is also based on the
Yeah, exactly same position. Yes, that we actually measure.
So will you be able to do multiple position when you are encoding the new audio as well?
It is possible. Yes, yeah. It can be. So actual recording is a bit more like hard work. You have to move around the speakers and microphone, right? But in virtual scene is very simple and easy. You can just move around like a game.
So that would work for 3D videos. So that would be better for 3D videos.
Yeah.
Move around.
Yeah, exactly. Like a computer games. Yeah. In computer games, you can just move around and then you can just listen the sound, proper sound from there, right? But they are from computer graphics model, fully just handmade one. Yeah. But this one is only from just one photo. But yes. But if you can make this kind of model here, I'll show the model later. Yes. Then yes, you can move around. I will show that one a bit later. So this one is dynamic rendering. This is a VR demo with one, and here there are 3 different scenes are rendered in one video. So this sphere is the location of sound source position, and then I will move around scene. But first one is only just 2D photos, 360 photos without any sound effect. And then I will add some like object of the scene and also show some empty rooms. Let me just play.
I just saw a gym near the new archaeological
Dry
museum.
sound.
I just saw a gym near the new archaeological museum. I just saw a gym near the new
If you
archaeological
have
museum.
headphone,
I
you
just
can
saw a
listen
gym
the
near the new
direction.
archaeological museum. I just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological museum.
Yeah. So without furniture, without object, you get more reverberation. Like if you just move out from your house, if you just remove all furniture and everything, then you'll be really surprised. And your room is really have a huge amount of reverberation there. Yeah. So it is something like.
Doesn't feel like home.
It is not really like home. Yes. Yes, so it shows that kind of comparison of just open space without any audio effect and the room with object, proper object, and then just a room boundary only. It's a shame that, but if you just probably some on Zooms, if they have headphone, probably they can listen that their sound direction and reverberation clear. Yeah, but here it is really hard to feel that, but just hope you can. So users can really move around like that and experience the scene. That's the scene the user is looking at with some sound effect with a VR headset, with some geometry or empty room effect. So that is kind of real demo system I had. That is clarinet, yeah, it's playing, and with some object. It's a bit old demo first. So you can just move around and listen to sound there. And here is a bit better. So it's with the proper texture and proper texture and geometry, a bit better detailed geometry rather than not just box model. And then here you can also see 2 different renderings. This one is just normal 2 texture without any acoustic effect. And the other one you will see from full 3D geometry with a proper acoustic effect. So, but I'm not sure how much you can
I just
repeat.
saw a gym near the new archaeological museum. I just saw a gym
Very
near the new
dry.
archaeological museum. I just saw a gym near the new archaeological museum. I just saw a
This
gym
is
near
the
the new
rendering.
archaeological museum. I just just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological museum. I just saw a gym near the
This is
new
again back to
archaeological
2D.
museum. I just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological museum. I just saw a gym near the new archaeological.
So with this one, you can feel a bit more full 3D geometry with texture and also sense of some acoustic property from the audio. So anyway, this one is made only from just only one photo. No other input, but just only one shot. So here, what I really try is a vision-based 3D structure and acoustic property estimation system, including some single-shot depth estimation, material estimation, and semantic scene completion, and 3D human pose estimation by Peter, and try to reproduce a plausible 3D audio-visual scene in real environment. So still, we have a long way to go. So we are trying to make some more realistic and useful applications like augmented reality or open air applications without headphone or with headset. We are also trying to apply for human robot interaction. And the more important one is more like subject evaluation of plausibility in VR space. So I'm working with some people in psychology. We have psychology departments who are also working on VR. I'm working with them for more like evaluation and also finding some perceptual link between audio together. So yeah, that is kind of rough introduction of my talk. Yeah, I'm not sure how much kind of information you can really get, and I'm not sure if they are interesting or not, but it might be good if you get any kind of small insight or some understanding of this kind of work.
Thank you so much.
Thank you.
Any questions?
Yeah, because I wasn't there last week, or the talk that you had the cross thing that was talked about. What is it? What is human tracking and policy measurement? What does it work inside the scheme?
All right. Okay. So roughly, this one, and another reason that I just removed that part is that currently their kind of VR headset already have some physical human tracker already, tracker of human headset. So without that part, it still works like that. But adding that kind of human tracking is more like a multiple human user interaction for that. So human tracking and pose estimation part, what we are doing is just only from just one single video, we have the human, but get some their skeleton data. So to understand their behaviors and their actions and their poses in 3D space from just only one single shot, photo or video. So there are lots of 2D human pose estimators like OpenPose or that kind of thing. So you can get some kind of scaling real-time tracking of 2D human, but they are still just on the video, 2D video. But Peter is working on like a 2D, 3D lifting. So if it's like a 2D pose like that, and then actually he's actually lifting 3D real pose. And then the extension of that will be understanding their behaviors and also getting them locations and then understanding their interactions. So that one is also linked to human-robot interaction. So like that, the robot can have a small camera on top of the robot, and then they can just monitor the environment so that they can some sense of depth, so that they are not really trapped in any kind of obstacles when they move around. And if they have some person, human, and they can also interact like a handshake or the passing some object to human, then they really need some clear 3D pose rather than just 2D. So that's the main topic. And then Peter is doing more like it is called the unsupervised learning technique. So just getting 3D pose from 2D without any kind of a 3D training data, because also getting 3D training data is very difficult. So that's what he's working on. There should be recorded.
Yes, we did. And we'll be putting this on the IMCC YouTube channel. Yeah, so it's usually to do that, but yeah, we'll be there. Yeah, anybody interested in that? Any other questions?
Can I ask a question?
Oh
Sure.
yes, from the virtual audience. Yes.
Yeah. Thank you very much for the talk. My question is that, so how can one represent a 3D sound? Because for 2D sound, I mean, clearly we have like spectrograms that we can use to train any system that we would like to train, but how can we represent 3D sound?
Right, okay. That's a good question. At the moment, we are relying on that kind of 3D rendering platform, Unity, because Unity, fortunately, it is designed for 3D game. So they have that kind of spatial audio rendering engine inside of that. So if we clearly define the source position and listener position, and also environmental geometry and their acoustic properties are preset, and then they can render the sound there from there. So in that kind of tool, it is relatively easy. We can just define the environment as like we design some 3D games. But in reality, if you want to generate some 3D sound, it is a bit more complicated because then we should go for, I'm not sure, this kind of a simulation stage. So we need to calculate all like reflections and then reflections and absorption of materials. And then we have to calculate and simulate the arrival kind of a signal to human ears. And also, we also have to consider there's another function like HRTF, head related transfer function. That is more like a personal function, that because HRTF is also different per person. It is kind of the way the signal is delivered from your outside of ear to your brain. Because the shape of your ears, and then the shape and length, and then thickness of the inside of ears are all different. So they are also quite personalized function, but we can measure it. It is possible. There's some measure. If you have some kind of a test, and then you can measure them, your own HRTF function. So we have to consider that kind of a simulation rendering and then make some final signal, which should be arrived at your 2 ears and then delivered to your brain. So it is a slightly a bit more complicated, actually. But there are lots of works are being done by acoustic researchers in acoustics. Yes.
Yeah, thanks a lot. I have another question on. So you mentioned that some for depth estimation. So sometimes you have quite scarce training data, and you, as far as I understood, might not have at all ground truth for your target domain, right? So how can you estimate the quality of your network on your target domain when you don't have any ground truth there?
That's true. So right, like that. Yeah. So yeah, in source domain we have ground truths, but in target domain we don't have any ground truths. Probably we can make a small set of ground truths, which is not enough for training, but maybe for testing. But anyway, the key idea here is, I did not really explain the details, but it is very similar to GAN. Probably you might have heard that. Yeah, have heard that kind of GAN system, like a generative adversarial network.
Yeah.
Fake news. You know, you have seen like lots of AI-based some fake news or fake human or fake photos, that kind of things. Yeah, they are all generated by GAN. So the main idea of GAN is you have 2 networks. One is generator. The other one is discriminator. So the role of generator is generating some plausible data close to the ground truth from some noise. So generating some plausible images by generator, and role of discriminator is to tell if that is real or fake. And they compete each other during training. So our goal is to train this generator to fool this discriminator, so that even the fake image, the discriminator cannot tell if that is a fake or not. So through that kind of process, generator can generate lots of fake images, which actually does not really exist. But people cannot really tell that it's real or not. So we adopted that idea to this domain adaptation. In domain adaptation, source domain, we have ground truth depth. So we train to this kind of depth estimation for source domain, but we add also target domain images. Then they shouldn't really work very well for target domain images because they are very different from source domain. So their depth estimation results should be very poor. That's for errors. But we also have same discriminator there. Discriminator try to tell, okay, the depth estimation result, this one should be source domain. This depth estimation result should be the target domain. It tried to tell which domain it is from. And this network is trying to fool this discriminator so that this generator, depth estimator, can generate very plausible depths even for target domain images. So they try to get some common features from two domains and then try to train the network, only use those common features only. So that generator, depth estimator, works well for source domain, or as it works well for target domain as well as source domain together by fooling this discriminator. So it is like a training process like that. So we can see that target domain depth is sort of plausible and then quite close to real one, but it is really hard to tell if that is really close to ground truth or not because we don't have them. But we can test it with some measurement.
But generally speaking, you just want to train a, let's say, generative model that takes that you condition on your target image, and you would like to predict a label. Yeah.
Yes, depth labels like generative models. Yes.
Okay. Thank you very much.
Thank you.
Thank you. Miriam, you want to ask a question?
Yeah, it was actually a follow-on question to the first one that the person online was asking. So maybe this is just a terminology thing. I think you said at the beginning that one of the things that you model has is ambient sound. Is that right?
Ambient sound, yes.
Yeah, so a lot of that is stuff that we filter out, don't we? Yeah, so we don't actually listen to a lot of the ambient sound. So how do you, I guess I didn't understand in the model, how you're deciding what to put in. It seems like all of the bouncing around noise goes in, but actually we filter out a lot of the noise, the ambient noise when we're
That's true, yes.
in natural life. Yeah, so yeah, could you just...
Yeah, okay, so there is a slightly different definition I use. Okay. So normally, yes, that's true. When we say ambient sound, it means background noise. Like when you're talking in a pub, then there are lots of ambient sound from other people, but you are just talking to other person, and then you want to just listen only to that sound only. Yeah. So that is called like a noise remover. There are similar terminologies here, like a noise remover or like intelligibility to get some only the speech signal only for the target you want. That kind of things, like or source separation. So like separating only that sound from that object from all other sound, that kind of thing. So yes, in that sense, ambient sound should be suppressed, to get some clear sound of that. But to get some immersive feeling and also realistic feeling of the space, we also need ambient sound. Yeah. So if we are just talking only on that person in a very private space, okay, I can listen. So clear delivery, yes, ambient sound should be removed. But like this kind of immersive feeling and a realistic feeling, you still need ambient sound. So some sort of ambient sound gives you the feeling like you are actually there. So it's your choice to add ambient sound or not. Yeah. So, but when I tell you about the ambient sound, there was it was from slightly different background. It is like when we encode the sound, it is like ambient sound is more like a mean sound of that, and then XYZ is more like a directional property of that. So it is slightly different, but
that's the impression I was getting. Yes, that your model is something to do with reverberation.
Yes.
But when you say ambient, I just want to clarify that.
Yeah.
Interesting.
Thank you. Any other questions? Yeah. I have a quick question. So you mentioned you work with psychologists. So could you give a quick summary of that?
That one is actually the human perception is still it is unknown area. So I feel like this, and then I say, oh, this is nice, or this is blue, but we don't really know this person is perceiving that it's the same as me or not. So so we have one academic called Christian Witcher. I'm mainly working with him, and he is working on that kind of color and object perception in psychology, and then testing it in especially on VR space with lots of artificial kind of additions and then removal of some factors. Because in VR you can have much better control of the factors in VR one. In VR one, to change the color, you really have to actually paint it by yourself. But in VR space, you can easily change the graphics there. So he used that kind of thing for human perception and what kind of factors are more important for better perception for human, and which one we can ignore that kind of part. So he's analyzing that kind of part, and my goal is also to just use the most important part, major part of that, and then just slightly just eliminating some other factors, because this one is the system is really heavy. It requires really heavy processing. So in that sense, I'm getting some help from here, this inside, and we are also planning. We did not really do that yet, but we are also doing more like a subject evaluation together, because they are very good at analyzing some subject evaluation with like questionnaires and analysis of data. I'm not very good at that kind of stuff. So we are planning to just arrange that kind of subject evaluation.
Fantastic. Thank you. Thank you. So I suppose if there are no other questions.